Microphone sorted out.
Underway right now.
All right, cool. So today what we're going to do is we're going to learn how to set up the voltage sensor and the current sensor, so we can measure the voltage of the battery and the current coming out of the battery, going from the battery into the motor control and then into the motor.
Yeah.
And this would tell us quite a bit of information about your card. One, it'll tell from the battery voltage, we can figure out whether the battery is fully charged, how much it is discharged down to, how is it performing, all these sort of things. From the current and the voltage, we can work out the power that's going into the motor. So these are two critical things in your design, knowing how much power you're putting, knowing how much current goes into the motor, and knowing the status of the battery. And if you can do these three as a minimum for your innovation challenge, you have a good chance of getting into that top 10 teams nationally. Right, so let's, before we think about that, in order to work out the voltage and the current and the power, we need to first think a bit more about programming. So last time we did understand a bit about variables, because that's how we discussed how a stopwatch can be built.
Yeah.
A variable holds numbers, and there are different types of variables in programming languages. So the simplest forms of variables, they hold integers. And you could, some of the integer type variables obviously include integer itself. There's a character variable, which holds an 8-bit number. So a number that has 8 ones and zeros in it. And then integers itself can be representing larger integer numbers. And then you go into variables like floats that can
Decimal point.
hold decimals. Yep.
I've done Python programming, so I have
Okay. Yeah. So it's similar across most programmings. Some in embedded programming you can. So if you have, for example, if you're defining an integer, you have also the flexibility to define it as an 8-bit integer or a 16-bit integer or 24-bit integer, just because you're memory limited. You could play around with the size of the variables. Also, you can have unsigned and signed variables. So an unsigned variable is where it'll count from 0. If you have an 8-bit variable, it'll count from 0 to 255. If it is a signed integer, it'll count from minus 126 to positive, minus 127 to positive 127. So this also gives you the facility to then have negative variables and positive variables. So variables is where we hold all our information in the program. Now, then we have things called logical or decision-making statements. So these decision-making statements, one of the classical ones is if and else statements, or if else statements. These kind of statements let us make decisions, which is quite vital in a program. So in a program, the two main things is you have variables coming in, and based on those variables, you do some mathematical manipulations, and then you use these logical statements to figure out some interesting things about these variables. So variables, decision-making statements, and then in order to make decisions, you need to be able to compare things. So there are operators that help you compare different variables. So one of the things is you can check whether two variables are equal to each other by using equal sign. Or you can check whether they're not equal, or greater than, or less than. So that's a neat way to check. If you have, for example, if you look at let's look at this example here. Let's say you have some pocket money, and we want to write a program to decide whether you have enough pocket money to buy an apple or a chocolate for lunch tomorrow. So we have a variable that holds the amount of pocket money you have. In this case, you had $3. we have two variables that each hold, one holds the cost of the apple, which is $2, and the other one holds the cost of the chocolate, which is $4. So what we had to decide in our program is whether you have enough money to buy an apple or a chocolate. And obviously for us humans looking at this, it's obvious that we don't have enough money to buy a chocolate, but we have enough money to buy an apple. In a programming environment, what you can do is to get the computer to think about this, we can use something called an if-else statement. So what we can check is, using the if statement, we can check if the cost of the apple is less than the pocket money you have. If that's the case, then you have enough money to buy the chocolate. Sorry, if the chocolate price is less than the pocket money, you have enough money to buy the chocolate, because that was the most expensive one.
Yep.
And then if not, we know apple is cheaper. We can compare and see whether the apple cost is less than the pocket money. And if that's the case, then you have enough money to buy an apple. You didn't have enough money to buy a chocolate, but you had enough money to buy an apple. Now, if neither of the conditions are met, if you had less than $2, that means you don't have enough money to buy either of them.
Yeah.
Now, that's an efficient way to write a program. Of course, you can write this program in a number of different ways. You could have said if chocolate money is less than pocket money, then you do something. Rather than having this else if statement, you can have if another if statement and another if statement. Now, it'll work exactly the same. The only difference would be the second approach would be much more computationally demanding. It'll have to evaluate each of those statements in the program. Whereas if you do this approach, it'll first check the first one, and if it meets, then it doesn't have to check the other two. So there are, once you practice programming, you would develop skills that'll help you write more efficient program that requires less memory, that requires less processing power, which will be quite helpful in the long run. Now, there are two types of logic operators that I should mention. One type compares the two variables itself.
Yeah.
And there is another one called bitwise operators. In bitwise operators, they compare one bit of the variable at a time. This is also important in some context, but it's a bit more advanced at this level, so I'm not going to dwell into that in this lesson. Now, the next thing we need to understand is, to be able to work out the voltage and current, we need to understand the difference between logic signals or digital signals and analog signals. An analog signal is a continuous signal that varies with time. It could take any shape. It can be a sine wave. It can be a triangle wave. The concept is that the value of the analog signal varies over time, and it's a continuous variation. It doesn't jump. If you compare that with a digital signal, the digital signal only exists in two different states. It's either a 0 or a low, or a high or a 1. And as the time goes on, the state, whether it's a high or a low or a 0 or a 1, would change, indicating your digital data. Now, we had to take this analog signal and convert it into digital in order for us to be able to measure the voltage and current using the microcontroller or the Arduino, and then process it using algorithms, using if-else statements, mathematics, in order to work out the power, the capacity, all these sort of things. Now, this happens every day in your computer. If you take the computer mouse decide the distance, the position it is in the analog sort of domain, and then converts into digital and send it to the computer as a stream of numbers. Same thing with your microphone, which you're listening to right now over. The computer gets digital data, converts into analog signals, and make it so that it hears you. And when I'm speaking to this microphone, it does the opposite, takes the analog information from my voice, converts it to digital, and send it to the computer. Now, of course, a real computer has a lot more advanced capability to do this. But also an Arduino has somewhat interesting circuitry that allows you to do this task. So you don't have to buy external circuitry to do it. So in the Arduino, there's a unit called the analog to digital converter. So it takes, as the name suggests, it takes analog signals in and convert them into digital signals. And remembering that a digital signal can be only a 0 and a 1, it represents the analog signal using a stream of digital bits, ones and zeros. Now, depending on how good this analog to digital converter is on a microcontroller, it has a maximum number of bits it supports. So it happens to be the one that's on the Arduino has 10 bits. So 10 ones and zeros that represent your analog signal. So if you had 10 bits, how many numbers can you count with 10 ones and zeros?
10 factorial?
It's 1023, yeah, minus 1, because you start from 0. So you can count from 0 all the way up to 1023 by having 10 different ones and zeros. Now, that means if you get a 0 voltage signal into the analog to digital converter or the ADC, that will be represented as a 0 number. And if you get 5 volts, it will be registered as 1023. Any number in between would be scaled based on these numbers.
Okay, so it's just rounded to the closest one.
Closest possible, yeah. So there would be some error. So let's have a look at how this would work with some examples, numbers. Before we do that, do note that the Arduino actually has 8 pins that are connected to the ADC. And these are numbered as A0 to A7 in your Arduino. So if you look closely on your Arduino, there would be, on one side of the Arduino, there are pins. Where's my Arduino?
So does that mean analog input and then digital output?
So you have A0 to A7 pins. They would all support analog inputs, but you can't. And then on the other side, you have D0 to D12. They would only support digital. So the analog pins can be used either as digital or analog. But the digital pins can be only used as digital pins.
Can I just quickly ask a question regarding the stopwatch? So since I connected the stopwatch to IO6 and IO7, the digital ports, does that mean that it won't be able to recognize the analog signals from the button circuit?
So the button works as a digital input because the button basically creates either a 0 or a 1. When the button is pressed, it creates a 1. If it's not pressed, it creates a 0. So it's a digital input.
Isn't it just letting all the energy flow from the battery, which is a...
it's a voltage. So you don't have, to have energy flowing from the battery, you need to have a current flowing. Because the Arduino looks like a very big resistor, it doesn't create much of the energy from the battery to flow into the Arduino.
Okay.
So it just basically makes the voltage of the battery appear across your pin, which is a high voltage, 5 volts, which is a logic high. And then when you release the press button, it creates 0 volts, which is a logic low.
So if I just want to make something that detects when a button's being pressed, I can just use the digital pins?
Yeah, exactly. Yeah. Okay. You only need to use the analog pins if you want to look at a time varying signal, like a sine wave, and you want to know exactly what are the voltages in the sine wave or represent the sine wave accurately.
Okay.
Okay.
The analog allows you to measure anything between 0 and the maximum voltage, anywhere in between that, where digital is just 0 and the maximum voltage is only 2.
Okay, I see.
Right, so A0 to A7 pins on the Arduino, they're all connected to the analog to digital converter, and they can be used for analog signals as well as digital signals if you configure them to be a digital pin. But you cannot use the digital pins, the D0 to D12, as analog pins ever, because they're not internally connected to the ADC converter. Now, let's assume that we take a A0 pin and we connect an analog signal into this A0 pin, and assume that that analog signal has a value of 2.5 volts. So if you put 2.5 volts, what the ADC does is, this has, in the Arduino, it has 10 different ones and zeros, which is a number that's 1023. It can count up to. Then what it'll do is it'll go and say, I know that 0 represents 0 count, and 5 volts represent 1023 count. Therefore, 2.5, which is halfway between, should be 1023 divided by 2. Which is not exactly, if you divide 1023 by 2, then it's a decimal number, right? 512.5. So it'll round it up or round it down. Usually it'll round it down. It'll be 512. And then what happens is, now you get this using a command called analog read in the Arduino code. So analog read would tell you, if you put 2.5 volts into the analog pin and use this command analog read, it'll tell you you have 512. Now, if you're writing a program, the 512 doesn't mean much. So within the Arduino, you need to now use some mathematics to convert this 512 back into that 2.5.
Yeah.
And how would you do it? You had to do the reverse of what the analog to digital converter did to achieve this. So what analog to digital converter did was, it took the number voltage here, it divided it by 1023 and multiplied by 5. Sorry, other way around. It divided by 5 and multiplied by 1023. Yeah. So to reverse it, you take the number you get, 512, and do the opposite, which is multiply by 5 divided by 1023. And you get a voltage 2.502. Now that you can see, there's a slight mistake in terms of what the Arduino would know in terms of the voltage, because you put 2.5, Arduino thinks it's 2.502. Yeah. This is called digitization or quantization error, which always happens in computers. So that's why when you go buy an expensive music system or an expensive headphone, they have more and more bits to do this. So more bits you have, the smaller that error would be. In this case, we have 10 bits, which gives a certain amount of error. But if I had 20 bits, it'll be even a smaller error. So that's why when you pay the price in terms of how many bits you have in your analog to digital or the digital analog conversion.
Yeah. So what are they typically with in audio to get really good sound?
I think audio starts around 8 bits and then goes to about 12. You could set. It also depends on how you process audio. Yeah. And you save like MP3 formats probably is an 8-bit signal.
Yeah.
But there is an option to set higher bit rates in audio processing.
Okay.
Typically, a lot of things tend to be around 8 bits, just because it's a sort of a trade-off between how slow. The more number of bits means much better accuracy, but also it means it's slower processing, because now you have to process so many bits more. That means you get accurate voice representation, but you're only getting less voice samples. So it either way it can be. So that's also the same thing with the number of megapixels in a camera. So if you look at a camera, it's not always good to buy the camera that has the highest number of megapixels in it, because that means more pixels means, again, less error in terms of the representation of the analog signal, but at the same time, it could introduce unwanted effects into the signal because you can't process all that data fast enough. So there's a balance between the number of megapixels if you're selecting a camera, megapixels versus the size of the sensor, for example.
So going back to the audio analogy, basically if you have less bits, will you have like sort of audio noise?
Yeah.
Yeah.
Like if you had a 4-bit voice versus an 8-bit voice, you would clearly see the difference.
Yeah.
And you could, I'm pretty sure if you go to YouTube and search for 4-bit audio voice, then you could see some samples. And then you search for an 8-bit or a 10-bit, then you would get some samples, and then you listen to those two, you would see the difference between the two. And you'd see the 4-bit is a lot more choppier.
And does that same sort of rule apply for like transmitting voice data over the internet?
Yeah. There are it gets a lot more complicated though when you're transmitting data over the internet, because always the data is compressed in most cases, and the compression itself does interesting things, and it might remove bits from the signals. So like, for example, if you were doing any audio or video editing using some software, it'll ask you what sort of bit compression do you want. You might have an original clip coming in as a 10-bit audio signal, and you might compress it down to 4 bits because it needs to be smaller.
Okay, I see.
Right, so now taking another example, let's assume we have 1 volt coming into that A0 pin. Now 1 volt would be 1 times 5 divided by 1023, which is a bit more than 204 point something, I think it was, from memory. So it's 1 times 5 divided by 123.
That's the other way around. Yeah.
Yep, way around. 1023 over 5. So it's 204.6. So you would get a number 205 in your Arduino when you do the analog read. And now you do the reverse, which is you take 205 multiplied by 5 over 1023. Again, you get a small error. So can you, by looking at this, can you tell me what is the error, maximum error you would get from this Arduino Nano?
It seems to be 0.002 volts of error.
Close to, yeah, it'll be 1 over 1023 because that's the smallest it can do. Right? So
that makes sense.
Actually 5 or 1000. So it's this number here, which is that divided by 2, because if it's higher than that, it always goes into the next bit, and then lower than that comes into the other side. So it'll be close to 2, just slightly about 2, 0.002.
Yeah.
Yep.
Wait, are you sure? Because when I do 205 multiplied by 5 over 1023,
yeah,
I get 1.001955.
Yeah, I rounded it up to, because I didn't have space to write it here.
Yeah, but instead of the error being over 2, it seems to be under 2.
For this specific one, but if there would be a number where you get this much error.
Oh, okay, yeah.
As the maximum.
Yeah.
In this case, yes, you're correct. It's 0.0019 something.
So is it worth worrying about that 0.002 volt error?
You would come to this when we talk about the current sensors. We'll come back to this and talk about it. So 0.24 is 2.4 millivolts, right? Remember that number, and then we'll come to that when we come into the current sensing.
Yeah.
Right, so proceeding, let's look at how to build the voltage sensor circuit. Now, the simplest and the most commonly used way to measure the voltage is using a voltage divider, like we discussed last time. And the reason is the Arduino can only measure voltages between 0 and 5 volts. And usually the voltage sources you use in your design, either 24 volts or 48 volts, it needs to be stepped down to be within that 0 to 5 volts. And the easiest way to do that is to use 2 resistors. So you drop the voltage coming in from the battery, 48 or 24 volts, down to about less than 5 volts. Depending on how adventurous you are, it can be close to 5 volts or a bit less than 5 volts. Okay. And how a voltage divider works is, let's give a really nice example. Les, do you want to give you an example?
Yeah, the voltage really indicates how much energy is available for the charge moving around there. And if you use, that's pretty loose, but anyway, reasonably true. And so if you come out of that positive terminal of the battery, Levi, and you go round the circuit to the negative, one of the principles of circuitry is that whatever energy the charges get at the battery is lost in one complete loop of the circuit before it comes back for more. So if it starts at the positive at 5 volts and goes round, it goes through those 2 resistors, then if they're equal in size, then each resistor will not only slow the current down, but it will take some of that energy away from the charges, transfer it to heat. So starting at the battery, positive 5 volts, when it gets round to the top of the resistor, no energy is lost, so it's still 5 volts there. Goes through the resistor, and if they're equal, then it'll lose half that voltage in the top one, drop from 5 to 2.5 at the middle, and then in the bottom one, it'll start off at 2.5 and then drop down to 0 volts as it goes through the second one. Are you happy about that?
Yep. Where so do you like set, do resistors just do that automatically, or do you get different kinds of resistors that do that?
Well,
no, you just set it so that so you basically you know that this needs to be less than 5 volts here at this ADC or the A0 pin if we connect it to A0 or the Arduino. And what you had to do is you had to figure out what is the maximum battery voltage you're going to get. So when the battery is fully charged, it might be 28 volts.
Okay.
Right? And then you decide this resistor and this resistor, so it brings it down to below 5 volts from that maximum battery voltage, 28 down to, let's say, 4.5 volts.
So
do you get specifically designed resistors for different amounts?
No, that's the point. Before you go back to the example I said, I was talking about 5 volts there, but if they're both identical, then you lose half the energy in each of them. So going through the first one, you lose 2.5 volts. Going through the second one, lose 2.5 volts. Going through both of them, you lose the whole of the 5 volts. You happy with that?
I don't quite understand how they know, so to speak, to take half of it. So if you put 100 volts in, would one of them then take 50 volts and the other would take the other 50?
If they're exactly the same size, yes.
Think about this. If you have 5 volts, and then you have a resistor and a resistor, each one is 1 kilo ohm in terms of resistance, right?
Yeah.
So there's a certain amount of charge flowing in the circuit when you complete the circuit, right? And that charge would dissipate a certain amount of energy in here and exactly the same amount of energy in here because it's the same resistance.
Yeah.
Now
it splits the voltage,
yeah. Because the energy is the same, it also splits the voltage exactly equal. And since the 2 voltage has to adapt to 5 volts, we know that if this is V, this has to be because the energy is the same. So we know that this and this has to add up to 5 volts.
Yeah.
That's the basic rule of sort of a closed circuit. So if we know that this is V, and this is 5 volts, then 5 volts has to equal 2V, therefore V has to be 2.5 volts.
Duleepa, could you just make that 6 volts? I'll show you. I know the point Levi's trying to make there.
Yep.
Can you just change that 5 to 6?
Yeah. So that's 6. Mm-hmm.
All right. So if the resistors were 3 kilo ohms each, then it would split the 6 as 3 and 3. You happy with that, Levi?
Yeah, I still don't quite get how it works, but it's electricity, it's black magic, so.
No. It's worth ironing it out because this principle is used in a lot of the sensors, and it's called a voltage.
Is it worthwhile teaching about current here, Liz?
Oh, if you want to, yeah. I just want to keep it simple to get the idea across.
So if you assume that you have an electrical circuit that has a certain resistance, R, and a certain voltage V, then it will create a current I to flow in this circuit.
Yeah.
Right? And Ohm's law say that this current is equal to the voltage divided by the resistance.
Okay.
So this is sort of a principle that's sort of the fundamental of electrical engineering. So current flowing in a circuit is the voltage across the resistance divided by the resistance itself.
Okay.
Now think about, and let's do an example. Let's say this is 5 volts, and this is equal to 1 kilo ohms. Okay. So my current in this case would be equal to 5 divided by 1 kilo ohm. How much is that?
5.
5, 1 kilo, 1 k is 1000, right? So 5 divided by 1000
So
is 0.005.
Yeah.
Right? 0.005 amps. Okay?
Yeah.
Now, if you put the same is true if you want to work out the voltage, you multiply current by the resistance and you get the voltage. Right? In this case, if you had 0.005 amps going through 1 kilo ohm, you get 5 volts. Which also agrees if you go around a loop, the voltage has to be dropping down to 0.
Yeah.
Now, let's go and add what Les mentioned. I'll draw it somewhere here. Now, let's say we have a couple of resistors, not just one. We have 5 volts coming in, and each of these is 500 ohms. Okay. Now the current going in through this circuit, it sees how much in total resistance.
Okay, so it establishes how much resistance there is.
Yeah. So this total is 1000 ohms, right? It's still 1 kilo ohm. So the current therefore has to be still the same 0.005. That means if you had 0.005 going through 500 ohms, this will be 2.5 volts.
Yeah.
And this will be 2.5 volts.
Yeah.
Right. Now, if I make this, say, I 10 times this resistance. So it will be 5,000 and 5,000. What would happen to this resistance? It will be 10,000, right? What will happen to the current?
It would get divided by 10.
Another 10. So you have another 0 here. What will happen to the voltage? It's still 2.5 because you added a 0 here and a 0 here, right? They cancel out. So regardless how many zeros you have in this resistance, or whether you divide this by each 10 or 2 or whatever, as long as they are equal, this voltage is equal across each of them.
Okay.
Because the current going through them is the same.
So is there any value in having resistors with higher ohmage or whatever you might call it?
Yeah. So that's why I'm explaining here. Now you want your sensor circuit to draw less current. You don't want to draw all the current in your battery from your sensor circuit.
Yeah. So the smaller your resistance, the smaller the current, and the less likely you are to burn things out.
Yeah. But you need to be also a bit realistic. So ideally, you want to keep it around a milliamp or 0.1 of a milliamp.
Yeah.
Now, if you're going a lot lower than microamps and nanoamps, then it's going to be quite sensitive. For example, if you sort of touch it, your body is also a resistor. It'll change your measurement.
Okay.
So you want this current to be around a milliamp, but not more than a milliamp is too much. More than a milliamp is too much. Somewhere between that 0.1 milliamp to a milliamp is about a nice number to aim.
So you'd go find and use resistors that give you that amperage.
Exactly.
Okay. I understand now.
So in this example, if you had 24 volts is what I have in this example. I have a 23 kilo ohm resistor here and a 1 kilo ohm resistor here. Now, if you do that, then it'll create 24 kilo ohms of total resistance, which means you have how many milliamps going through the circuit?
5/24.
23 plus 1 is 24.
Oh, wait.
So 24 over 24 is 1 milliamp, exactly.
Yeah.
So if you had 1 milliamp going through 1 kilo ohm, how much voltage do you have across that voltage, across that resistor? 1 milliamp and 1 kilo ohm. I times R?
I times R, so 24 multiplied by 1, 24 volts.
No, across this bottom resistor, there's 1 milliamp. So you have a resistor that's 1 kilo ohm, and there's 1 milliamp going through it.
Yep.
So that would be, voltage would be equal to 1 kilo ohm times 1 milliamp. How many volts is that?
1 volt.
1 volt.
Okay.
So if you had a 1 kilo ohm and a 23 kilo ohm, you connect 24 volts, you get 1 volt out.
So it works kind of like fractions.
Exactly. Yeah.
So if you had 24 volts
Mm.
and a 16 kilo ohm resistor, then an 8 kilo ohm resistor, would you get
8 volts?
Yeah. Okay.
Oh, yeah.
If the bottom one is 8, it depends on which one is 8 though. So if you swap them around, you'd get whatever the bigger one has the bigger voltage.
Yeah. So is it fractional?
Yeah, it is a fraction.
Okay,
yeah.
I see.
So,
yeah, that makes sense.
And you can use this equation if you want to calculate it on a calculator. So basically, the battery voltage times the resistance on the bottom one divided by the total resistance.
Voltage equals. Oh, I multiply that out. Okay.
That's why it's called a voltage divider, Levi, in that it takes the input voltage, and depending on the size of one resistor compared to the other, it will split the incoming voltage in that proportion.
Yeah.
Part of it will be lost in the top resistor, and then part in the bottom. And the midpoint there between the resistors will therefore have a voltage that is input voltage minus what's lost in the top one.
Yeah.
And
so you could achieve the same effect as the 16K and 8K by having 3K and 1K.
Yeah.
Yeah.
Oh no, 2K and 1K.
The same ratio, basically.
Yeah. Okay, yeah. So, okay, awesome. So ratio.
The only difference between the two is if you had the smaller resistance, there would be more current going through the sensor, and therefore it'll be wasting energy from your battery, which you can use to drive.
Okay, yeah.
Yep. So now let's, by the way, today's Proteus file is on the website as well. So if you go to EVolocity and go to examples, there's Arduino module 2 file. If you can download that and open it.
Did you say that was, Duleepa?
The website is nevelocity.github.io, and then go to examples.
EVolocity.
Yeah, nevelocity.github.io.
EVolocity module 2, I assume.
Did you find it, Les?
I haven't yet. Yep.
Cool.
So what's it called?
So you go to examples, and then the second one, Arduino module 2 example.
And that's the code.
That's the Proteus file for today's example.
Oh, is it? Okay.
Yeah. So you can click on that link and it'll download it to your computer. Did you get it?
Yep. You just click on the link, do you? Or
Yeah. Click on the link. It should download it as a zip file. No?
haven't got it yet.
Did you get it?
No, not yet.
Are you on this website?
Yeah, I can't access that because I'm recording.
Sorry?
I'll have to access it later because while I'm recording, I can't disturb the screen.
Shall I send you on the messages the link?
Yeah.
Let me.
So in Proteus, you can select the resistance of.
Yeah.
Okay, cool.
So on the Zoom chat, I sent you the link.
Okay. Yep. Got that. See you, Bill.
So if you go and download the second set of files, module 2 files. And you should have this circuitry in front of you. You good, Les?
Yeah, just keep on going. I'll be right.
Cool. So
Thank you.
let's, Levi, have a look at this circuit where we have the 24-volt battery, and then we have a voltage sensor made up of 23 kilo ohms and 1 kilo ohm. So we know from our analysis that this has to be 1 volt. So let's run the simulation and confirm that it is 1 volt. So if you press run, you see you have 24 volts coming in. You're producing 1 volt as the sensor output. And you have 1 milliamp going in through this circuit because you have 23 and 1 kilo ohm adding up to 24 kilo ohms, which is 1 milliamp. Now, we can test your hypothesis by adding 10 times more resistance, right? You can double click and add another 0 to both resistances. Now they are 230 and 10K. We know that this should not change the voltage. It should still be 1 volt from the sensor. But it's lowered the current to 0.1 milliamp, which is nicer, but you had to be a bit careful in practical terms because the sensor is now drawing a lot less power, a lot less energy from the battery, but it might be tricky to build it.
Yeah.
Now, if you wanted to have more volts, what would you do? You change the ratio, right? So if I make this 20,
you need more amps.
It'll be still the same because it still adds up to the same.
Yeah, more volts
right?
in the sensor.
Now you have 4 volts. That's 4 over 24 times 24. You get 4 volts. Okay.
Yeah.
Right. So that's how a voltage sensor works. So you can just buy 2 resistors, very cheap. They're like 10 cents at most or 50 cents at most. $1 would get you a voltage sensor that you can make for your battery.
So do you buy the resistors with the resistance pre-installed, so to speak? So you just go find, so you use Proteus to find the golden ratio to get between 0 and 5, then you go out and buy those resistors? Okay.
Yeah. But also keep in mind that people don't make resistors for every single value there is, because then there would be billions, millions of resistors, right? They make them in very discrete numbers. So you might have to compromise between what you think is the best and what you can buy.
Yeah. So if I just put in a ratio 6K to 1K, 6K on the top, 1K on the bottom. So would that be suitable for between 5 and 0?
6K to 1K would give you 1/7 of the voltage coming in.
Yeah. So I want to turn the 24 into a less than a 5, right?
Yeah.
Okay.
But 24 might be your nominal voltage when the battery is half flat.
Okay.
So depending on whether you have a lead acid battery or a lithium battery, this can be quite a bit different.
Okay. You should probably ask Liz because he's I believe.
Are you using the lead acid batteries or the lithium batteries in your card?
Oh, I think Levi will have lead acids here.
Okay.
Okay.
So those lead acids probably would go up to about 26 volts less
Okay.
when they're fully
Approximately.
charged.
Yep, yeah, fully charged they will. Yep.
And then it'll come down to about 20, 22 when they're fully discharged.
With no current on, yeah, probably, yeah.
So you design it so that 26 volts would be less than 5 volts.
Yeah. Okay.
Okay. Right. The next thing is we need to figure out how to measure the current. Now, there are multiple ways to measure current, but one of the easiest is to use something called an IC, or an integrated circuitry. These are small circuits that all built into one package. You just buy it and put it and it works, sort of things.
Yeah.
There are many different integrated circuits that you can buy to sense current. In this design, we are going to have a look at something called the ACS 712. It basically has two terminals where you pass the current through. So you break open the circuit, you insert the current sense and allow the current to flow through this integrated circuitry. And it produces an output voltage that represents this current. And the reason for this is your Arduino can only measure voltage, not current.
Yeah.
So you had to take the current and convert it to a voltage so that the Arduino can measure it. And this IC would let us do this. And it happens to be, now this IC produces output voltage that's 2.5 volts plus 0.066 times the current.
Yeah.
Now, if you think about that, now that's 66 millivolts per every amp. Now, if you're ADC, we said the accuracy was 2 point something millivolts.
Yeah.
So 2 point something over 66 is a reasonable error. It's not too big, but it's still reasonable. So it's not something that you can ignore and say, well, you can ignore to some extent, but not fully ignore it. In this project, you don't have to do anything, but in a real, like if you were designing, let's say, a real car, then you would actually worry about it. So basically, as an example, if you had 10 amps going through the motor, through this IC, then the output would be 10 times 0.066, which is 0.66, plus 2.5, so it'll be 3.16 volts from the sensor.
Yeah.
Now, also these integrated circuits, being circuits, they need power, energy. So you need to supply a 5 volts and a ground to this IC chip when you use it.
Yeah.
And that's reasonably doable because you already have 5 volts coming into the Arduino, so you just take that 5 volts and connect it to this integrated circuit.
Yeah.
Now, let's start now developing some code. Before we do that, let's have a look at this, how it works in Arduino Proteus, just to sort of clarify that this actually does work as what we wanted. So I have set up a circuit here which has the ACS 712. I have the same 24 volt battery, and I can change the value of the current by changing the value of this current source, and therefore having different currents going through my IC.
Yeah.
So what we decided, or what we determined, was that this would produce a voltage that's 2.5 times the current plus the current times 0.066.
Yeah.
Let's see whether it actually does work. So if you run this, 1 amp should produce 2.566 volts. Rounds it up to 2.57. Now, if I change the current, double click on this, I can change the current. I can make it 10 amps, for example. I could say there's 10 amps flowing through the circuit now, and it produces 3.16.
Okay. So then you get the amps from the volts, you would minus
2.5 and then divided by 0.066 to get the amps. Yeah. So you had to do the reverse operation for both sensors to figure out the actual value. Okay, now that we know how the two sensors work, let's go and write our first software to work out these numbers. So I'm going to zoom this out so we can see it. And I'm going to open up a new Arduino document. And I'm going to also bring up what we wrote last time. Where is it? Here we go. So we have the two files that we did, new file for this week and file from last week. I'm just going to copy and paste my initial introduction to the code, the comments that talk about the code. And I'm going to say this is Arduino module 2. And this does the voltage and current measurements. Voltage and current measurements. Right, in the setup, what we're going to do is we're going to use the same terminal printing capability so we can see the numbers we are getting. So we're going to copy and paste that serial begin and the serial print stuff from the previous code. Don't need that one. So we need initialize our serial so that it can print information that we would calculate later on. Okay. And I'm going to test this code to make sure it works and it prints that it has initialized the serials and communication works. I'm going to verify this program, and before that I can do that, it'll ask me to save it. I'll say example 2. Okay, I'm going to save that, and it verifies the sketch. And then what I can do is I can go into the Arduino, show where the example 2 is. Again, reminding it's in the C drive. We created a folder called Arduino Outputs. It's in there. So we open that up, press OK. Now we are ready to run. So if we had done this properly, it'll show a command saying serial comms with PC initiated.
Have I got the right .elf?
So we got the communication initiated. That's all good. Now the next thing is, now we want to read the voltage that's coming out. Let's start with the voltage sensor. Voltage sensor. Now we want to connect this to ADC 0 here, or A0.
Yeah.
Now, obviously we can draw a wire from here to here, which is going to be really ugly. So I like things to be neat and nice. So what I'm going to do is, I'm going to do this trick here, where I'm using two labels, so it connects up the output of the voltage sensor to ADC 0. So I don't have to draw wires. This will nicely connect them up together without cluttering the circuit. Yeah. Okay, so now I'm going to read the voltage I'm going to get from my A0 pin. And to do that, I use the command, we talked about this, analog read. And the pin I'm reading is A0. Now we have to store it in a variable. Now, what is this analog read? It's going to give me a number between 0 and 1023.
Yeah.
So we need an integer to store it, right? It's an integer number. So we are going to create an integer variable called voltage read, and this is equal to analog read. Then I'm going to print this voltage, serial.print voltage is serial.print line. I'm going to print whatever I read here. Okay, so I read the voltage.
Might want to put quotation marks around the voltage to make it a string.
Oh yeah, thank you for that. And over here we are reading Right. So we would expect now, in this case, what did we have about 4 volts to be read? 4 volts would be some number close to 1023. So we would expect that to be displayed. Let's compile this, verify it, and run the code and verify that we get this number.
So my one, once again, isn't printing to the terminal. It isn't printing anything, in fact.
Can you double click on the terminal and make sure it's 9608, none, 1, and no? Do you see the terminal?
Yep.
Are you using the code program that you downloaded from the internet, or you own one?
I'm using the EVolocity module 2, the downloaded Proteus.
Did you put the right program, direct it to the right program?
Sure do. It's only one Arduino mod 2.eno.elf.
Okay. So this line isn't printing either?
No.
Can I see your computer?
Yep. I've got the code there.
Give me a second. I'll zoom so I can see you better. Serial. Again, serial print. Yeah. Okay. That looks correct.
Compile all that and then go to here and select ino.elf on a mod 2 and then run it.
Do you see the terminal window appearing?
No.
Okay, so go to debug in the screen. So go here, debug.
Yep.
Let me run. So you're running the simulation, right? First run the simulation, and then go to debug, and then there's the fourth one, virtual terminal.
Oh, okay, yep, now it's working.
Cool. All right, so now it's showing as 819. Is this correct? So do we expect this here, 819? Let's double check it. So what we have is 4 volts coming in times 1023 divided by 5, 818.4. So it rounds it up to 819.
Yep.
So that makes sense. Now we want to actually take this and convert it to an actual voltage. So let's do that by now when you put an actual voltage, it's going to be an integer or a floating number?
Float.
It has to be a float number because it's a decimal number, right? So the variable we had to use is a float. I'll call it actual voltage equals the voltage I read times 5 divided by 1023.
Yeah.
Now, if I do this, I would not see anything. Try it out. There's an error in this program. So verify it, run it. Hold on. Actually, you had to change this to actual voltage. It actually works, but only for very specific cases.
Yeah.
To do it properly, what you had to do is you had to have 5.0 here. It tells the Arduino, when you do the division, also do a division, not assuming an integer, assuming a floating number or a decimal number. So that's the proper way to do it. So if you do that and run it, you will see the results are slightly different. Maybe not. there would be there would be numbers that it would not work. If I change this slightly around, let's see. If I go to like 4.1. It's 4.09 volts. If I didn't have that's 0, I think it should not work. Yeah, there you go. Can you see the difference now? So if you, it should be 4.09 volts. But since I don't have that 0.0 here, it doesn't show me that decimal place anymore.
Yeah.
So if I put that decimal place in here, it would work properly as expected and be more accurate. Right, so now I can measure the voltage. But I still don't know the battery voltage. I get the voltage at this point. So how do I convert this to the battery voltage? You had to do the inverse of this sensor, right? So the sensor basically divided it down by 4/24. You had to multiply it by 24/4 to reverse it back.
Yeah.
So let's do that. And again, it's going to be a floating number because it can be a decimal place. So battery voltage is equal to actual voltage we read times 24 divided by 4. So I'll change this to...
You need to use brackets in any of the equations, or does it just do it from left to right?
So there's a strict way it does it. Because I'm using simple statements, multiplications, and divisions, this is fine. But if you start having more complicated ones, then you do have to use brackets. So actually, if I did this technically correctly, I should be using this, like this. Right?
Yeah.
Now, if I now run this, now, oh, I haven't changed the changing that battery voltage. I'm going to change. I might change the battery voltage slightly, so there's a decimal number in the battery voltage. I'll make it 24.2.
Yeah.
So we can see a bit more exciting numbers rather than...
So what do you got in that last line there, Duleepa? You've got serial.print line.
Battery voltage.
So it's BATT.
V, yeah. So that's the final voltage I calculated. Yeah. So now I get 24.22 volts. That 0.02 volts been coming in as an error.
Yeah.
Right. Now this is good. I don't want it to go crazy on the conversion, so I'm going to put a delay term in here and delay it by about a second so it doesn't print it all the time. So I'm just improving the code slightly to do this. So now every second displays the battery voltage.
Yeah.
Right.
And you don't really need to do that for a computer, do you? You can just, computers can handle.
But you still want to, because the more calculations you do in your computer, the more power it draws.
Ah, okay.
So in terms of efficiency, you want to try and minimize the number of calculations you do.
So there is
just enough.
Delay in there. Okay, awesome.
Right, now we want to calculate, we know how to do the voltage. Now let's go and do the current. So the current, we know how it works. We know that it produces 0.066 volts per every amp. So basically we had to reverse it. So to do the current, first we'll read the current from A1, which is connected to A1 now. So we're going to use the same statement. I'm going to say int I read and analog read A1. And I'm going to print this so that I can see my current. I'm going to put the delay right at the end, so it just both together, voltage and current. And that'll be current read. So I have 10 amps. So it's 10 amps times 0.066, which is 0.66, plus 2.5, I should read 3.11 volts. Converted to a scale between 0 and 1023, I should get roughly about half of 1023.
Yeah,
So
I got about 627.
Okay, that sounds about right. I'll verify mine as well. And this is a good thing to do when you're doing programming. Write one step at a time and verify, because you have the simulator. It's a luxury that you can do this step by step. It helps you a lot in terms of troubleshooting. Okay, so we get 647. Now we want to convert into a voltage. It's the same process. It's a float now. So I'm going to replicate, copy and paste what I did for the voltage and change it to the actual current now. Actual I is equal to I read times 5.0 over 1023. And I'm now going to print actual current. Actual current read. Verify it. Run it. I get 3.16, which is exactly what this voltage source is showing. The multimeter is showing me.
Yeah.
Cool. Now I want to revert it back and figure out exactly what the current is. So to do that, I had to apply the reverse of what the sensor did. So
take off 2.5 and divide by 0.66.
Exactly. Yeah. So I'm going to create, copy and paste that. Battery current is actual current minus 2.5, right?
Yep.
Now you had to use a bracket, otherwise it would get confused. Divided by 0.066. 0.066. And I'm going to say battery current.
So I got 76.52.
What's that?
I got 976.52. That doesn't seem right.
I get 10 amps. You might have missed something somewhere.
Int read current is analog read A1. Oh, maybe it's because I put the entire equation in brackets.
Did you use 5.0 here? If you don't use 5.0, it'll give you an error, because it thinks that because this is an integer, it thinks it works with integers and it doesn't divide it properly.
Okay.
So 5.0 is a very important thing in getting this right. It has to have that 0.0.
Yeah. Okay. So I need to initialize a float, then use the float.
Yeah. If you use this as a float, then that's fine. Otherwise, you need to tell the Arduino program that it needs to be a float when you do the calculation.
Yeah.
In programming, this is called a term casting. Does it work now?
Yeah, I'm just quickly. Okay, semicolons.
While you do that, I'm going to change the current to 30 amps and see whether it works. Oh, actually make it something a bit more exciting, like 20.65.
Now we've got 3.16.
3.16.
Yeah.
Can I have a look at your code?
Yeah.
It's a bit actual current, read current 5.0. That's correct. A1. It should be 0.066.
Oh. Okay. 0.066. Slight little mathematical error.
Should work now, I think.
Oh, I don't think I gave it enough time to verify the code. Still getting 3.16.
3. Did you change the printing value? You might have not. You might have not changed the variable.
Yep, that's it. Whoops. There we go, 10.83.
Cool, nice. Right, so now we got basically out of this, we got the voltage and the current measurements working using some dummy battery examples, right? Next step is we need to put this into our actual motor controller and the battery system.
Yeah.
Now, what we can do is, or what I have done here is I have created a model that mimics your car.
Yeah.
So you could run this and observe what happens. The variable sort of thing up down here lets you set the speed. So you can press these buttons, and by pressing it, you can change the speed of the motor you can see here. It shows the RPM. So you can also click here, click like that. This is your accelerator basically in your card. So higher the accelerator, you press it further, faster it goes. You release it, slower it goes. Now observe the current and the voltage of the battery as you change the accelerator position. When you start going faster, it draws more current. The battery voltage dips a bit because of the internal losses in the battery. And then if you go slower, battery voltage first goes negative and then slowly goes down to a smaller value, and the battery voltage comes up again.
Yeah.
So that's expected behavior of the battery. The only thing that this one is not modeling is the battery discharging, because it's a bit harder to model. It can be modeled, but it might be too extensive to run on a computer if you don't have a good computer. So I haven't modeled that part, but everything else is modeled as it should work almost in the card.
Yeah.
So you have the battery here. I see that I have made a mistake. It should be battery, not motor. Then you put your sensors here that you worked out. The voltage and the current sensors goes in here. Then we had the motor controller that you would learn with Les soon. And then you had the motor that goes into your card.
Yeah.
So from our sensor, what we're doing is we're measuring the voltage across the battery and the current coming out of the battery.
Okay.
So the challenge for coming week, so this is the end of this session today, is to first take these sensors from what we have done today, put this into this actual circuit that you would have in the card. You can just, to copy and paste, you can do this. You can go here, copy, and then you can paste it if you wanted to copy and paste.
Yeah.
Same thing here. You can copy and paste this one and put it in the right place.
Yeah.
If you wanted to draw it again, you got all the components that you need in this. If you go on the component, and then you got resistors here, you got the ACS 712 here. You can redraw it yourself as well.
Okay. Yeah.
So either is fine. You can copy paste or you can redraw yourself. So the challenge is first copy and paste or redraw the circuitry in here, and then connect them up to the Arduino A0 and A2. But remember to disconnect it from here. Otherwise, both signals would come into the same place and it'll not read the right values.
Yeah.
So you connect it onto the Arduino. The software you have written should work, but improve it so that it can read power 2.
Okay.
So how do you figure out power? Power in a circuit is equal to the voltage times the current.
Okay, yeah.
Do we know the voltage? You already worked out the voltage.
Yeah, well, we can figure it out.
You already worked out the current. So we just have to put another statement saying float power equals battery current times the battery voltage.
Yeah.
Okay. So you do that, and then you can print the power, voltage, and current coming from the battery. Then what you do is you can also improve this. Now, we said that there is 2.5 volts in this signal here.
Mm-hmm.
But when you buy the IC, it's not exactly going to be 2.5 volts. It might be 2.55, it might be 2.45, or it might be even 2.4. So there might be quite a bit of error because of this. Because if you take 2.4 and divide it by 0.066, that's a huge difference compared to 2.5 divided by 0.066. So usually if you're designing this, you would actually measure that voltage which is coming onto this pin here, pin 6 of the IC. So you would use another ADC pin and measure it and use it in your calculation rather than using blindly 2.5.
Yeah.
Okay, so that would be the challenge for this coming week for you to do.
Yeah. Sweet.
Right. Les, are you there?
Yep, I am. I'm just very quiet.
So that's it for today, Les.
That's cool. Thank you for that.
All right. So we should, now the students should have enough information to basically build the voltage and the current. And while you're here, Levi, we are in the process of, let me get out of this first, building a circuit that you might be able to use in your design. So I'll show you how it looks like if you're interested to see it. So
would this be providing us with a printed board?
Yeah, it's a printed board where you can connect up the Arduino. It already has the ACS 712 and the voltage divider, and connects it onto the Arduino itself, A0 and A1 pins. You connect the battery up here from this end, you connect your control on this end, and you load the program. It'll already be able to load the program you've written and be able to print all the voltages and currents and power. And also it has a header here that you can connect up to your Bluetooth module, the LCD panel, and also a Bluetooth module that you can connect up here.
I get the distinct idea that you have a lot of fun at your job.
It's good, yeah. So Les and I am working on how to get this manufactured, because the university is not. Last year we manufactured it at university and produced it to the students, but this year, because the university is still half operational, we don't have the resources to build it. So we are looking at options in China right now. So hopefully we can get it done in time. Right. Anything else, Les, you wanted to add?
No, I will close that video off now, and which means that is that code in that you've put on there? Is it available in the?
So I would make the code available today. So I didn't make it available until I finished the lesson, so the students can write it with me, and then I would put it on.
It's just I know I've been asked by someone else to
Okay.
make it available, so that'll be good.